Good morning, students. Let us start the class today. Has anybody found the answer for the question which I asked in the last class? We have been generating this particular matrix instead of polynomials, and we had discussed those problems of using polynomials also. That is when I told you the Kannada proverb, Podya Pishachindra, Bandegavakshili. That was the one I had told in a jovial manner. So, for that purpose only, we had all these factors, g of x, x into g of x, x squared into g of x, x cubed into g of x. Using that, we could write this generator matrix. And we had already discussed in the last class also that g of x and h of x both have to be a factor of x power n plus 1. Now, this particular generator matrix does not contain an identity matrix, but basically we want to have a generator matrix with the identity element. So I was asking you that revise your basic knowledge of your linear algebra and tell me the answer. What should we do now for having a standard format of generator matrix? Can anybody tell me today? All right, Kuldeep has given the right answer today. That is row transformation. Row transformation means we will have to have some linear operations now. We will have to have some, just a minute, I am connecting the charger to my laptop. Okay, so we will have to perform row transformation, or we will have to perform some linear operations. And that is why I had asked you to revise the knowledge of linear algebra, which means in a matrix, when we perform some linear additions, linear subtractions, they are called linear operations. Whenever we perform such operations, the actual matrix value is not going to change. That was already studied by you in maths courses. So now we will have to perform a linear operation such that we will have an identity matrix at the right side. Let me correctly write the line here. Yeah. At the right side, we should have a complete identity matrix. At the left side, we will have a parity matrix. You can see 1 0 0 0, 0 1 0 0. We should have 0 0 1 0. Then we should have 0 0 0 1. In that case, complete right side is going to be an identity matrix. G can be of the order of 4 cross 7 in this manner, where it is first 3 columns correspond to the parity matrix, next 4 columns correspond to the identity matrix. So now how do we transform this particular matrix? It is easy now. Now the generator matrix has to be in the systematic form of P concatenation. Let me use that name concatenation here, and it is the symbol called pipe. P with the pipe symbol in between with IK for the case of cyclic codes. As the above matrix is not in the systematic form, the same has to be transformed into P piped with I4 form by means of elementary row operations. So let us perform some elementary row operations. You can see the example here. R3 equals R1 plus R3. Again using the modulo 2 addition. R3 equals R1 plus R3. Then R4 equals R1 plus R2 plus R4. When we do that, R3 equals R1 plus R3. Here we have 1 0 1 0. Now we want to get 0 0 1 0. So we will simply perform R3 equals R1 plus R3. R1 plus R3, 1 plus 1 becomes 0. But you can see here 1 plus 0 is 1. 1 plus 0 is 1. And 0 plus 1 is 1. So you can see here this row became 1, 1, 1. 0, 0, 1 became 1, 1, 1 because of R1 plus R3. Now here again 1 plus 1 modulo to addition, it is 0. 0 plus 0, 0. 0 plus 1, 1. And 0 plus 0, 0. That way we have this third row now 1, 1, 1, 0, 0, 1, 0. So we got one third element which is part of identity. The last one is R4 equals R1 plus R2 plus R4. R1 plus R2 plus R4. So 1 plus 0 plus 0, that is 1 here. Let me underline this. Again 1 plus 0 is 0 because it is R1 plus R2 plus R4. 1 plus 1 plus 0, that is 0. Next again 0 plus 1 plus 0, that is 1. Next we have R1 plus R2 plus R4, that is 1 plus 0 plus 1, that is 0. Then we have 0 plus 1 plus 1, that is 0. Then 0 plus 0 plus 0, that is 0. Then we have 0 plus 0 plus 1, that is 1. So by means of these two row operations, by means of these two, how do we decide on these two? Only by visual inspection. We have no other go. We will have to visually observe how each row can be transformed into an identity. What we want is, here already we have 1, 0, 0, 0. We have 1, 0, 1, 0, 0. Here we want 0, 0, 1, 0. For obtaining 0, 0, 1, 0, what should be performed? That should be visually observed and then decided. Similarly, for this 1, 1, 0, 1, we want 0, 0, 0, 1. That is why R1 plus R2 plus R4. Now you can see the left side elements of the third and fourth are also changed by means of these linear operations or row operations. Now we have this generator matrix in the form of identity matrix as well. Now here the parity matrix is already obtained. When we convert the generator matrix into the standard form, parity matrix is obtained, that is 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1. That is the parity matrix. So hence the systematic cyclic code vectors can be found using the formula C equals D into G. That means now we have the generator matrix. Now using the particular data vector, we can actually find out all the code vectors. Means we need not go for polynomial multiplication. That is the great advantage here now. We have been finding it difficult in polynomial multiplication, polynomial division. Of course, multiplication was easy, division was difficult. Now when we define a generator matrix even for the cyclic codes, life became much easier now. So now you can see the code vector can be obtained by means of the data vector into the generator matrix. So that way, I have already tabulated all the code vectors now. The code vectors are as follows. For all the code vectors right from 0, 0, 0, 0 till 1, 1, 1, 1, it is computed using this matrix multiplication and then it is listed here. Now, you already know what is the Hamming weight of each of them, number of ones which are present in the particular code set, code vector, that is called Hamming weight. I have listed the Hamming weight for all of these code vectors. Now you can see that minimum Hamming weight is 3 in this case, which means, coming back to our Hamming weight, Hamming distance and error detection and error correction abilities, here the minimum Hamming weight is 3. That means it can detect 2 errors, d min minus 1. D min is 3. That means it can detect 2 errors, d min minus 1, that is 2 errors, and it can correct only 1 error, d min minus 1 divided by 2. 3 minus 1 divided by 2. 2 by 2 is 1. So this particular scheme can detect 2 errors and correct 1 error. In the sense, the syndrome which is available for some errors may not be present in the parity check matrix at all. In such a case, we will be able to detect the error at the receiver, but we will not be knowing the position of the error, so we will not be able to correct the error. That is the idea which we had seen earlier also. So let me proceed. Now we have a generator matrix at the transmitter. Similarly, we can have a parity check matrix at the receiver. It is also called as Hamming matrix. The generator matrix was constructed using the generator polynomial and its factors, means g of x, x into g of x, x squared into g of x, x cubed into g of x in the previous case. Similarly, we have h of x also, right? Now, h of x is also a factor of x power n plus 1. That we are using h of x, we can construct the parity check matrix which will be useful at the receiver. That means whatever properties we had when we discussed the block codes, the same methodologies are applied even for cyclic codes now. Even though we wanted to completely discard the matrix operations, then we found out that polynomial operations can be more complicated than the matrix operations also when it comes to large numbers. So then whatever we learnt in the block code set, we are going to implement the same with the cyclic codes also by implementing parity check matrix as well. So in a similar fashion, h of x can be used to obtain the parity check matrix as follows. Now this is slightly a different procedure. Now, as I have been telling you again and again, the proof for all these operations is beyond the scope of our syllabus itself. But as they say in the proverb, the proof of the pudding is in eating it, right? In the same way, let us not worry about the mathematical proof. Let us only think about how to use all these in our applications. So as we had g of x along with the multiplication of x, x squared and x cubed, here the procedure is slightly different. The product of h of x is defined now as x power k into h of x power minus 1. Now remember, this x power minus 1 is not 1 over x. This is simply a notation. Let me highlight it. Now this x power minus 1 is not actually 1 over x. It is not h by s. It is h of x power minus 1. That means the whole polynomial will have its reciprocal. Remember that. It is not 1 over x. It is reciprocal of the whole polynomial. So the product h of x is defined as x power k into h of x power minus 1, which is also a factor of x power n plus 1. Now the great mathematicians who worked out on the information theory, they have found out that all these products are also factor of x power n plus 1. That means that particular term x power n plus 1 itself is going to yield g of x also, h of x also. Now these reciprocal products up to x power n minus 1 into h of x power minus 1 represent the parity check polynomials. These products can be used to construct the parity check matrix in the order of n minus k cross n. We will see an example, there you will understand it more clearly. Let us consider the 7, 4 code for which h of x equals x power 4 plus x squared plus x plus 1. See, h of x is given here now, x power 4 plus x squared plus x plus 1, or we can also write it as 1 plus x squared plus x power 4. Now, h of x power minus 1 is what? I told you, it is the reciprocal. Reciprocal in the not that order. It is not just 1 by 1 plus x squared plus x power 4. It is written in this manner. 1 by x power 4 plus 1 by x square plus 1 by x plus 1. That means the reciprocal of each term is taken there. Okay. That way you will have to visualize. That is why I told this is a notation. H of x power minus 1 is not h of 1 over x. It is a notation. However, you can take it as h of 1 over x in this manner, that each term in the h of x is written reciprocal. Now, the parity check polynomials can be written in the binary form up to the degree of 6 now. How? We can see this way. See, in the case of generator matrix, we had gone up to x, x square, x cube. Now we will go x power 4, x power 5, x power 6. Now you can see x power 4 into h of x power minus 1. You can multiply x power 4 to this term. Anyway, it is visible now here. We will multiply x power 4 to this term now. When we multiply x power 4 to this term, x power 4 divided by x power 4 is 1. X power 4 by x square is x square. X power 4 by x is x cube. And x power 4 by x power 4 is, x power 4 by 1 is x power 4. So that way we have now 1 plus x square plus x cube plus x power 4. This is the parity check polynomial. Now this can be written in the binary form. We have 1, then we have for x square we have 1, x cube we have 1, x power 4 we have 1. X is not there, so it is 0. X power 5 is not there, it is 0. X power 6 is not there, it is 0. That is why I told you up to the degree of 6 now. So we have 1 x power 4 into h of x power minus 1, that is 1 0 1 1 1 0 0. Similarly, multiplying the same h of x power minus 1 by x power 5, we get x plus x cube plus x power 4 plus x power 5, and its corresponding binary representation is 0 1 0 1 1 1 0. That 1 is not there, then x square is not there, then x power 6 is not there. That is where we have written 0 and all other terms are 1. Lastly, x power 6 into h of x power minus 1 is x square plus x power 4 plus x power 5 plus x power 6. That is 0 0 1 0 1 1 1. 1 is not there, x is not there, x square is there, x cubed is not there, then x power 4 is there, 5 is there, 6 is there. That way, now we have 3 binary vectors. Now these 3 binary vectors can be written in the matrix form. Now parity check matrix H itself can be written in the order 3 cross 7 using these 3. You can see here 1 0 1 1 1 0 0, 0 1 0 1 1 1 0, 0 0 1 0 1 1 1. Now this also should contain an identity element. For containing an identity element, we will have to perform the linear operations. Now for the cyclic codes, the parity check matrix has to be in the systematic form of I n minus k concatenated with P transposed. Now you can see here P transposed. Let me write a line here. Now this has to be P transposed. The right side is supposed to be P transposed. Left side we are supposed to have identity matrix, but that's the order of n minus k. So the above shown matrix has to be transformed into I3 in pipeline with, not pipeline, pipe symbol with P transposed. So I3 concatenated with P transposed by means of the row operations. So we will simply perform one row operation, R1 equals R1 plus R3, because we have this 1 0 1 0 1 0 0 0 1. That is 1 0 1 has to be transformed now. So we will simply perform R1 plus R3. When we perform R1 plus R3, we get 1 0 0. R1 plus R3, 1 plus 1, 0. So here it is 1 plus 0, 1, 1 plus 1, 0, 0 plus 1, 1, 0 plus 1, 1. So at the top you will get 1 0 1 1. Right? Yeah, at the top you will get 1 0 1 1. So you have got 1 0 0 1 0 1 1, then 0 1 0 1 1 1 0, 0 0 1 0 1 1 1. Now this is the identity element and we can verify this. This is nothing but P transposed. That we can verify. Let us verify. See, P is here 1 1 0 0 1 1 1 1 1 1 0 1. Let me remember 1 1 0 0 1 1 1 1 1 1 0 1. 1 1 0 0 1 1 1 1 1 1 0 1. Let us see that. Now you can see 1 1 0, sorry, P transposed is here 1 1 0 0 1 1 1 0. I think it is matching. I don't know. It must be matching. 1 1 0 0 1 1 1 1 1 1 0 1. Yeah, in the transpose form it must be accurate. All those 4 rows are here as 4 columns. So it is matching that way. Here, right? Correct. 110011111101. It is matching here after the row operations. So this matrix can be used for generating the syndrome vectors at the receiver. Please recall, in the 4th module we have been using such matrix for generating syndrome vectors. Now it is the same type used for cyclic codes also. This is about how to use even matrices in cyclic codes, in the case of cyclic codes. Now let us continue about the hardware implementation of these processes. In the previous module also we had seen how to implement by using hardware about syndrome generation or about code generation. Now similarly, let us study now about how to generate using hardware about all these polynomial operations. For obtaining R of x now, we want to have a remainder polynomial, right? For obtaining R of x, we have to perform the division of x power n minus k into d of x by g of x. Now, this division can be accomplished by means of the following circuit now. Considering g of x to be of the form 1 plus g1x plus g2x square plus g n minus k minus 1 x power n minus k minus 1 plus x power n minus k. Now this g1, g2 up to gn minus k minus 1 are the coefficients for the particular terms, which means if g1 is 0, x is absent. If g1 is 1, then x is present in the polynomial. That is the idea here. Now let us see how to implement this division using shift register without using dividers. If you start using dividers, hardware becomes more complicated. But as I have been telling you earlier, binary algebra has many strange inherent properties within. So that way let us see. Now you can see we have these registers R0, R1, R2 up to Rn minus k minus 1 we have registers. And all these G1, G2 and Gn minus k minus 1, they are shown as buffers. They are like on-off gates. In the sense, you have already studied fundamental CMOS VLSI now, right? You know about transmission gates already. So you can visualize the G1, G2 up to Gn minus k minus 1 as transmission gates. Transmission gate in the sense, if this is 1 and if this has to be turned on, this can be turned on. If G1 is controlled, whatever is at the top will come at the bottom. That's all. It is like transmission gates or simply switches. Now, in the polynomial, if x term is present, then there will be this gate at G1. Similarly, if x squared is present, there will be this gate G2. Otherwise, they will not be there. But below, we will have registers. Single bit registers R0, R1, R2 like that up to Rn minus k minus 1. In between them, we will have these XOR gates for modulo 2 operation. Now you can see at the input, there is one XOR gate and there is this D of x and then there is this AND gate. Why are we doing all these things? Because we are going to generate the check bits using the data bits themselves. So you can see here, this D of x is initially connected to the position of 1 in this SPDT switch. Such switches are called single pole double throw switches. Now this switch is called SPDT, single pole double throw. Initially this switch will be at position 1. So whatever is the D of x, that is going to go to the channel. You can see this side is the channel. Output of the channel encoder now is going to be the channel. So initially, as we are dealing with the systematic code vectors, initially let the data bits only go. Then later on let the check bits go. Now let us generate the check bits using this architecture. That is the idea. As we are using shift registers here, or we are using registers in a serial fashion here, that is when we call them as shift registers. Basically they are registers only. We are going to use them in a serial fashion now by giving clock pulses. Now in this particular circuit, clock is not shown. You will have to visualize the clock, and you will have to visualize that for every one clock signal, one bit is going to arrive here. D of x is going to arrive here. That is how you have to visualize. For the first few clock pulses, let us say if we consider the 7,3 code, then for the first 3 clock pulses, this switch will be connected to position 1 only, and all the data vector will go there. D of x will go there respectively for the first 3 clock pulses. At the same time, whenever that each bit is coming here in the first clock pulse, it is input into the XOR gate, and its output is coming here. The XOR gate's output is coming here. Initially all these registers are 0. When all these registers are 0, for the first 3 clock pulses, whatever is the data coming here, that is going to come here to this AND gate. And let me tell about the enable pin later on. Whenever we enable, whenever we disable, let me tell you later on. Now you can visualize, let us say in this D of x, first one is 0, as this is also 0, output is 0. Let us say this is 1, and this is again 0, output is 1. Again, let us say this is 1 or 0 or whatever. For the first 3 clock pulses, as all these registers are 0, output of XOR gate is same as the input at that time, right? You already know the output of the XOR gate is 0, 1, 1, 0. So that way, when one particular input is kept at 0, whatever is the input to the other pin, that is going to be output there. So that way it will come here. Later on we will see how those bits are utilized using this enable pin. But understand, in those 3 clock pulses, they are gated into the circuit, and that is where something is going to happen. When first D of x is coming, it is going to channel at the same time, the same D of x is input into this shift register block, and we have the polynomial represented in the shift register block. So accordingly, those bits are stored in the particular registers by means of this modulo 2 operation. And later on, let us say after 3 clock cycles, later on the switch position goes to 2. When the switch position goes to 2, later on for the 4th, 5th, 6th, 7th clock cycles, the output of the registers is going to come here. It means accordingly for each clock pulse, there is going to be this XOR operation, right? Or modulo 2 operation. Based on that operation, that check bits are going to be generated by this hardware, and serially one by one those check bits are transmitted to the channel, and at that time the position of the switch will be connected to 2. This is the basic idea of generating code. Okay. If you did not understand it fully clearly now, you don't have to worry. Later on I have an example. Using the example I am going to discuss further. There you will understand it in a much better way. Let me proceed. This is a brief explanation. Here R0, R1, R2 up to Rn minus k minus 1 are the flip-flops that make up a shift register. And G1, G2 up to Gn minus k minus 1 are the gates which close if Gi is 1 and are open if Gi is 0. That means in the generator polynomial, if that term is present, then this gate will be present. Otherwise, this gate will not be present. They are like buffers or transmission gates. That's all. Now the steps are, initially all the flip-flops are reset, and then enable is kept high, and the switch is kept at position 1. This condition will remain for the k clock pulses. This is the first step. All the flip-flops are reset, enable is kept high, and the switch is kept at position 1. This condition will remain for the k clock pulses. That is when all these input pulses will be gradually transmitted to the channel. Now message input is applied with dk minus 1 at the first clock pulse, dk minus 2 at the second clock pulse, and so on until d0 is applied at the kth clock pulse. Please remember MSB first here. Message is applied with MSB first at the first clock pulse, then later on until LSB is applied at the kth clock pulse. Now, as the switch position is at 1 only, the data bits gets transmitted into the channel in the same order. Means MSB goes first, LSB goes last. After k clock pulses, enable is kept low. Why? Already the data bits are transmitted to the shift registers and they are already there in place along with those XOR operations. So now enable is kept low. When enable is kept low, the AND gate will not work later on. So later on, whatever happens at that data side, it does not affect our shift register. So after k clock pulses, enable is kept low and the switch is kept at position 2. This condition will remain until the total clock pulses become equal to n, after which the register is reset. That means once the total clock pulses become equal to 1, those many bits have been transmitted to the channel. Now the register can be reset and the next code vector can be taken. The next data vector can be taken. So at the end of the kth clock pulse, the register contains the parity bits which are transmitted to the channel in the next clock pulses. That means that XOR gate arrangement and the shift register arrangements automatically generates that parity bit. That is the beauty of the circuit now. How is it going to happen? Let us see in the example. So at the end of kth clock pulse, the register contains the parity bits. One by one, all these parity bits are again transmitted. That is why you can see here Rn minus k minus 1's output is connected to this, directly to this position number 2. You can see here that is connected to position number 2. But at that time it does not affect our AND gate. Why? Enable is low at that time. Purposefully enable is kept low so that it will not affect further. There is no feedback later on. But initially feedback was supposed to be there. Why? Initially all the registers are 0. That way this first XOR gate is there. Let us see the function of the very first XOR gate only when we see the example clearly. So now at the end of the kth clock pulse, the register contains the parity bits which are transmitted into the channel in the next clock pulses. In G of x, as G0 and Gn minus k both are 1, there is no gating required for them. Hence G0 remains connected and Gn minus k remains disconnected, as we require only R of x, the quotient Q of x in the serial form gets discarded. Without actually performing the division, we are going to get a remainder polynomial here, and that division is going to happen automatically there by means of that hardware. G0 remains connected. Why? Because the very first term is always 1, right? 1 plus x square, that way it goes on. So when there is 1, there is no question of it becoming 0. But if that is not there, then let us see in the example what is going to happen. Let us say this 1 itself is not there in the generator polynomial, then this register itself need not be there, right? That let us see in the example. That is why there is no gate here. It is directly connected. Similarly, anyhow the last term has to be present, right? Whether the last term is present in the polynomial or not, it has to be present as far as our architecture is concerned. So for the last one, there is no gating. See, this is the last XOR gate. You can see for each register, there is this XOR gate. For the first register, first XOR gate. For the second register, second XOR gate. That way it goes on. Now this was for this one. Now for the last register also there is XOR gate. This XOR gate is for the last register only. Modulator operation is there for all of them. But the point here is there is no gating required, because by default it has to be present in the architecture. Okay, whether that term is present in the generator polynomial or not is different. In the generator polynomial it is going to be 0 only there, isn't it? That is different. But otherwise there is no gating required for the first one and for the last one. Anyhow, this will be clear when we discuss the example. So in g of x, as g0 and gn minus k both are 1, there is no gating required for them. Hence g0 remains connected and gn minus k remains disconnected. As we require only r of x, the quotient q of x in the serial form gets discarded. Hence, the hardware for the encoding of a systematic cyclic code consists of a n minus k bit shift register. So many flip-flops. Now n minus k modulo 2 adders at the most. Somewhere in between, we may not require them based on the choice of generator polynomial also. That's why it is written as at the most. And an AND gate with the 2 inputs. And a counter to keep track of the operations. Why a counter? Because only those many clock cycles should be given to this particular hardware. So we need a counter. If at all we connect 7,3 channel encoder, in that case we have at least 7 clock cycles. So those 7 clock cycles have to be counted. So we need a counter. That counter is not shown in the block diagram. So as is evident, this hardware is much simpler when compared to that of n minus k linear block code. Remember that we had discussed the linear block code hardware implementation where we had large number of XOR gates there, and here we have shift registers. Along with that we have at the most n minus k XOR gates. So as is evident, this hardware is simpler when compared to that of n minus k linear block code. That is the advantage of cyclic codes. We will see the example now. I may not be able to complete this example today. Let me see how much ever I can cover, let me cover. In the next class, let us revise it again. Now, for the 7,4 systematic cyclic code, g of x is 1 plus x cubed. Write the encoding circuit and show the steps for obtaining the code vectors for the following message vectors, considering 0101, 1010, 1001. We are discussing 7,4 systematic cyclic code, means 4-bit data vector and 3 check bits. Now we have this generator polynomial 1 plus x cubed. Now let us write the encoding circuit for this. Let us see how code vectors are generated. Now given G0 is 1, G1 is 1, G2 is 0, G3 is 1. See, given G0 is 1, 1 plus x cubed. 1 is there, x is there, x squared is not there, x cubed is there. So G0 is 1. I think you can see here. Let me annotate. You can see here now. G0 is 1, 1 is there. G1 is 1 because x is there. X squared is not there, so G2 is 0. And x cubed is there, so G3 is 1. That way we have G0 1, G1 1, G2 0, G3 1. Now using this we will have those many gates. As I told you already, G0 will always be 1 this way. In here right now we have 1. Now the encoding circuit is like this. You can see G0 is present, G1 is directly shorted. Even though in the main block diagram we showed it as a gate, here we have directly shorted because the generator polynomial is known now. And you can see the first flip-flop's output is connected to an XOR gate. Now G1 is connected to the XOR gate. Next G2 is not there. When G2 is not there, you can see here. What is the point? There is no connection here. There is no gating here. When there is no gating here, no need of XOR gate here, right? What is the point in connecting when XOR gate will not have a particular input? It will be 0. The other input will be 0. So between R1 and R2, it is direct short. Last one, G3 is anyhow 1. That anyhow 1, this XOR gate is there by default. That I had shown you earlier. So now we have R0, R1, R2, 3 shift registers, and we have only 2 XOR gates. You can see that. That way this circuit is quite simple. Now let us see for the very first example 0, 1, 0, 1. For the first 3 clock cycles, what is going to happen? 0, 1, 0, 1. So it will come as 1, 0, 1, 0, right? Because first MSB comes, last LSB comes. He has given the example 0, 1, 0, 1. I am writing it in this fashion 1, 0, 1, 0. Or let me see. Let me write 0, 1, 0, 1 only. Why am I confused? I am confused actually. Sorry. So let me write 0, 1, 0, 1 only. So let me write 0, 1, 0, 1. Now for the first 4 clock cycles, 0 goes here, then 1 goes here, then 0 goes here, then 1 goes here. This 0 is going here, this 1 is going here, this 0 is going here, this 1 is going here. For the first 4 clock cycles, and enable is 1. All the registers are reset, so it is 0 only for the first clock cycle. Okay. Now this 0 is coming here, and we have 0 here, very first 0. So output here is 0, output here is 0. Now that 0 is coming here, and that 0 is coming here. I hope I am correct. First 0 is coming here, register is reset, here it is 0. So output XOR gate is 0. Enable is 1 also, but AND gate output is 0. So here it is 0, here it is 0. This register was earlier 0. Now that 0 is here because it is shifting. Earlier this was containing 0, that is here. Now this register was containing 0 here, that 0 is shifted here. Okay. Now this is 0, this is 0. 0 is again 0. Output is 0. The present input for R1 is 0. The previous state of R1 is now present output as 0. That is coming out at R2. So next bit that is going out here is again 0, right? Because that is the present one. Now in the 4th clock cycle, what is going to happen? Let us see later on, not now. Maybe not in today's class. Maybe in the next class only. But what I am telling is, this 0 is now gone here. At the same time, this 0 came here. Everywhere 0 only got stored. Now this 1 came here. This 1 is now going here. Okay. That 1 came here now. Let us see. Let me stop annotating. No, I cannot stop annotating. Anyhow, it is all 0. Let us assume that way only. Now, let us say I have this 1. This is 1. This is 0. Assuming this present output here is 0, here it is 0, here it is 0. Okay. Sorry, I did wrong here. This should be erased. This is now 1. So the previous state of R0 is coming here 0, and let me remove this. Now this 1 came here, this 1 is coming here now, that 1 is coming here now. So now the previous stored state of R0 was 0, now 0 and 1, this became 1. Okay, the previously stored R1 is 0 here, R2 is 0 here. So again, the next output also will be 0 only. but I am talking about the second clock pulse. Okay, this output is not coming to the channel. Even though R2 is giving the output at that time, that is not going to the channel because switch is connected to position 1 only even now. I am discussing the second clock position now. Now in the third clock position, what happens? The next one is 0. But we have to remember that this R1 is now containing 1 and R0 also is containing 1 now. R2 is containing 0. We have to remember this way. R1 is going to contain 1 because input here is 1. R0 is containing 1 because input here was 1. So 1, 1, 0 is going to be stored. So let me stop annotating. Let me write that here. 1, 1, 0. Now that is the state present in R0, R1, R2. Next, the third cycle is coming. In the third cycle, this is 0. But this is 1. This is 0. So when this is 0, input to R0 is 0. But output of R0 is 1 here now. But this is 0. When this is 0 now, 0 XOR 1 is 1. Now that 1 got stored in R1, that 1 is coming here. And that 1 is coming here. But that 1 will not go here anyhow. That 1 will not go here anyhow because switch is connected to position 1 only. But now we'll have to remember that in the next cycle, R0 is going to have 0, R1 is going to have 1, R2 is going to have 1. That is the next cycle. Now coming to the fourth cycle. Let me remember it is 0, 1, 1. It is now 0, 1, 1. Now in the fourth cycle, it is 1 here. This is 1 here. This is 1 here. So that 1 is now coming here. And this 1 is coming here. Now this 0 is coming here. This is 1. This 1 is coming here. This is 1. This 1 is coming here now. So after the fourth clock cycle, what are the contents of the register? Contents of the register are 1 and 1 and 1. All the three are going to contain 1. Now, in the fifth clock cycle, enable will become 0. Now, in the fifth clock cycle, enable has become 0. Later on, all 4 data bits are there. But right now, this is stored as 1, 1, 1. But this is going to be 0. So this is going to be 0 for all the next 3 clock cycles. This is going to be 0.